So this experiment is investigating the motion of a roller on an inclined surface. We're provided with a roller which contains a bolt and 2 washers, shown in this diagram. We're told to measure and record the distance x, which is between the 2 washers. And basically, yeah, so this is our large washer and this is our smaller washer, and the distance x is the distance between the two. Now, I have written down that it is 22 millimeters long. So really for this, when you do this experiment, it should be within, let me change the color of this pen, within the range 20 to 24 millimeters. And it makes the most sense to use millimeters because it's a really small distance and there can't be any decimal places because you have to ensure that the value you have given matches the precision of the ruler used, and the ruler only does it to the nearest millimeter. Any values to the nearest centimeters are not awarded, and a lot of people, what they did is, oh, that's the next bit. So yeah. Okay, now it asks us to measure and record the diameters of the larger and smaller washers, okay? So the diameter is all of this from a line that goes through the center. A lot of people make mistakes where they'd only measure the radius, which would only be half a diameter. The diameter is going to be the whole thing. For the larger diameter, the mark scheme has given us a range of 38 to 42 millimeters. So I've gone with 41 millimeters, and the same rules apply. It should be to the nearest millimeter, no decimal places. For the smaller diameter, no range has been given, but just going based off of the diagram, the smaller diameter seems like it's close to half the size of the larger one. Okay, dokie. Then it tells us to calculate L, where L has this formula. So our small x multiplied by our large diameter divided by the difference between the large and smaller diameter. When I substitute my values in, I end up with a value of 28. Okay? Then it says to justify the number of significant figures you have used for your value of L. Significant figures. Well, if we take a look at the significant figures of the quantities in the formula, they're all two significant figures. So, naturally, L should have, or should be, just 2 significant figures as well. Then it asks us to place a flat board onto a bench and support it with a wooden block so that the board is at an angle of approximately 10 degrees to the bench. And then it asks us to record our degrees or our angle. We'd use a protractor to measure this, and we should end up with approximately 10 degrees. It's okay if it's a bit more or a bit less as long as it's close, okay? Okay, then it asks us to place the roller onto this board and wait until it is stationary. Then push the roller to one side and then release it. This will cause the roller to oscillate, and then we're told to take measurements to find the period of the oscillations. So what I did is I carried out 2 repeats and I timed it for 10 oscillations, and I used a stopwatch that recorded to the nearest 0.1 seconds, and I did this twice. So the first time I got 6 seconds for 10 oscillations, and the second time I got 8 seconds for the oscillations. So we need the time taken for 1 oscillation. So obviously what we're going to do is we're going to divide the time by the number of oscillations. And since we got 2 different values, I'm going to take an average by adding the 2 and dividing by 2, because there's 2 values in our average. If we did 3 repeats, this would be divided by 3. And the sum of all values on top, and then we end up with 0.7 seconds, okay? Now, to gain the marks for this question, we had to do at least 2 repeats. Because it's worth 2 marks, you need to put in a bit more effort than you would with a 1 marker, for example. your times have to be either to the nearest 0.1 seconds or 0.01 seconds. This would be in accordance to your stopwatch. So whatever it gives you, however precise it is the value you'd be expected to use. And also has to be within, or what is expected is that your t value is within 0.2 to 0.5 seconds. Wait. Oh, my bad, sorry. No. It is meant to be within 0.5 to 2.5 seconds. Yeah, that sounds more right. And we ended up with 0.7 seconds. Okay. Then it asks us to calculate the percentage uncertainty for our value of t. Okay. So how do we calculate percentage uncertainty? It's the absolute uncertainty of whatever device we are using over the measurement we have made. Okay, so what we've used is we've used a stopwatch to record the time, and our stopwatch was to the nearest 0.1 seconds. So we have a minimum absolute uncertainty of 0.1 seconds. However, this is unrealistic. We're actually likely to see an absolute error of 0.2 to 0.5 seconds. Given the conditions of the experiment, we haven't really done that many trials. To be fair, the marks scheme does allow for you to have half this range as your uncertainty if you've carried out multiple repeats. But I've still chosen to go with 0.2 as my absolute uncertainty, only because 2 repeats is still not really that much. And it's always better to be on the safe side. So when picking your absolute uncertainties, you have to consider the nature of the experiment. An estimate like 0.1 is way too low. And then obviously I divided by a measurement with 0.7 seconds, times it by 100, that's part of the formula, and we ended up with a 29% uncertainty. Okay. It then tells us to use the spanners to loosen the 2 nuts either side of the smaller washer. We need to move these nuts and the smaller washer along the bolt until X is as large as possible, and then use the spanners to tighten the nuts. So basically, this is going to move further back. Okay. Now it's asked us to repeat our measurements. So I went with, this is inaccurate, I just went with values that were okay to use in calculations. So obviously my X value must have increased because we've increased the distance between the 2 washers. So I went with 32 millimeters. And then when I input this into my formula, obviously, which was this one right here, my D's, my diameters, remain the same. However, X is now 32 millimeters. So I end up getting an L value of 57. And then I recorded a T value of 1.2 seconds. For this T value, actually don't need working out, but always do put your working out. Or you don't need repeats, but do make repeats. If you have time, of course. To get these 2 marks, you'd need your 2 values, and you'd also need your second T to be greater than your first T. Now this makes sense because you've increased the distance. Now the washers are further apart, and the rolling of the roller is going to become a lot harder, so it's going to rock more slowly back and forth. So the oscillations are going to be a lot less in a lot more time, if that makes sense. It then suggests a relationship between T, L, and X and puts them into this formula and asks us to calculate our values of K. So remember all your values for your first experiment and then your values for your second experiment, and simply input them into the formula. A lot of people struggle with rearranging, and a lot of people do forget to square your T, or forgot to square their t in the actual exam. So k is being times by t squared here. So to rearrange it so that k is the subject, you, instead of times, you're going to have to now divide. So all of this is going to be divided by a t squared. And you need to familiarize yourself with where the power of 2 button is on your calculator. And I ended up with these two k values, 35 and 28. It then asks us to explain whether our results suggest or support the relationship that's been suggested. So for these types of questions, I tend to go with percentage difference. We have two values and we calculate the percentage difference between the two. To calculate the percentage difference, you take the absolute value of the difference between the two values and then over the average times 100. So our 35 minus our 28 over their average, because 35 plus 28 divided by 2 is 31.5, and we get a percentage difference of 22%. Now you have to make your conclusion, and you have to specify what calculation you carried out and what values or quantities you were using in this calculation. So I used my k values to find a percentage difference and see whether or not they're significant. So you can make both arguments. I argued that yes, 22% isn't that high of a percentage. It's significant. Actually, I did put in brackets, but so you can argue yes, 22% is a pretty significant percentage difference. Therefore, the results do or do not support. So, if it's significant and it's a really distinct percentage difference, then no, they don't support. But if it's not, then yes, they do support the relationship, because the difference between the two k's is not that big of a deal, because obviously the relationship suggests that k is a constant. I mean, by looking at the two values, 28 is not that far from 35, so I would argue that 22% is not significant, so my results do support the relationship suggested. Okay, then it says an approximate value for the acceleration of free fall, denoted by g, is given in the following formula. Use your second value of k and your value of theta from b, which was the 10 degrees, to determine g. Now, it's good to have some background knowledge. G is approximately 9.8 meters per second squared. So we should have a number close to that at least. So when I input my data into this formula, I end up with this really huge number. And knowing that this is the value we're looking for or looking close to, this seems ridiculous. So hopefully you recognize that this is actually in millimeters, because remember, our values early on to determine our k were in millimeters. So that's why we will actually end up with millimeters per second squared rather than meters per second squared. So to go from millimeters to meters, you just divide by 1,000 like so. And I get 6.4 meters per second squared. This is not too close to 9.8. That could be because the data I used was made up values. However, I know that they are both in the ones, so I know that I've done something right. Okay, then it asks us to describe the sources of uncertainty or limitations of the procedure for this experiment. And then, of course, it follows up with improvements that we could make to this experiment. So it's good if you can link the two. So a couple of suggestions are things like 2 readings is not enough. This is a common one, but you can't say that they're not enough alone. You have to say that they're not enough to draw a valid conclusion, or else you won't get the mark. There's difficulty measuring the diameters, which is true, because I think the main reason is the bolts or the nuts prevent the placement of the ruler. Because if we go back to the diagram, we find that it's not just this flat surface, there's this in the way and this in the way as well, so that's a valid reason as well. Another thing is theta is so small, there's a large uncertainty. 10 degrees is very small, which would lead to a large percentage uncertainty. D, oscillations die quickly. This could be for a couple of reasons. One, honestly, a roller is not going to roll on for that long. And down here it says the roller slips down the road. Slips down the board. It could slip down the board, which would affect the way they oscillate, the way it oscillates, and it could also end oscillations a lot faster. Another thing is difficulty measuring time, as with stopwatches. It's not just a matter of human reaction time, but it can also be difficult to judge when an oscillation has started or ended. So for the fact that we don't have that many readings, just take more and plot a graph. Don't just take more, plot a graph. Or you could, for example, compare K values. Then for the ruler, you could use a caliper. For example, instead of a ruler, to measure the diameter for more accuracy, you could increase theta, so there's reduced uncertainty. Percentage uncertainty. You could increase the number of oscillations by, for example, using a smoother material so that they can go on for longer instead of a rough surface, which would stop them a lot sooner. And then for the timing and not being able to identify when oscillations have ended or started, the use of a fiducial marker would definitely help. And then last but not least, another method of reducing slipping, so this would actually be the opposite of this one right here, and that is to use a rougher board so it wouldn't slip down the board. Now, I think I only have 2 comments in regards to this. Always state your quantity and reason to gain the mark, or else you won't get credit for a point you make. The second thing that was mentioned in the examiner's report is many people suggested that using the protractor wouldn't give you an accurate angle because it couldn't be aligned with the bench surface. However, this is incorrect because it is possible to measure the angle of the board at any height above the bench. So that's just something to note down, and that's it.